It's my great opportunity to be invited to speak at this wonderful conference, and I would like to thank the organizers for this great opportunity. I'm going to report some recent results I did together with Professors Fong, Song, and Sturm on the geometric estimates on Kahler spaces. Well, my talk will consist of three parts. Mainly, I will focus on the second part. If time permits, I will give you some outlined proof on the main ideas of the results, in the proof of the results. So the first part is on the background and motivation for the reasons why we study this kind of problems. And second, I will explain the main results. The first subparts on the smooth Kahler spaces, and then on the singular Kahler spaces. Well, now let's first look at the backgrounds and motivations. Let me explain or fix some notations that I'm going to work on. First, we let X be a compact complex manifold. And here, omega x is a fixed Kahler metric, smooth Kahler metric. Well, if you're not familiar with the Kahler manifolds, you may simply understand this X to be a complex manifold. A complex manifold is simply a differentiable manifold equipped with integrable complex structure. We always assume the boundary is empty. So this is a compact manifold, or more precisely, a closed complex manifold. And we fix the dimension of the manifold as n. Here, n, I mean the complex dimension. It has real dimension 2n. In local coordinates, in local holomorphic coordinates, a Kahler metric can always be expressed by Gij bar, with the basis dzi and dzg bar as the local basis of 1-1 form on the complex manifold. And here, Gij bar, the local coefficients of the Kahler metric, explicitly it means that locally it is the positive definite matrix at any point, and also is the emission matrix, by the way. Well, this omega x defines a global 1-1 form, and it is called Kahler. Usually it's called emission form or emission metric. It is called Kahler if additionally we require that this 1-1 form is closed. Closed means the D, here D is the standard exterior differential. And locally, this is equivalent to these local equations involving the ordinary derivatives of the metric coefficients. Essentially, it means that if we view this as a three tensor, even though it's not a tensor, if we view this as a three tensor, it just means the indices with bars or unbars are symmetric. Well, one of the main advantages for studying Kahler metrics is that the Ricci curvature of the metric is very simple to be expressed in local holomorphic coordinates. The Ricci curvature is simply equal to the dd bar of the log of the determinant. Determinant is simply the volume form. So the Ricci curvature is essentially, the local potential of the Ricci curvature is essentially the volume form. The volume form, a determinant of the Gij up to certain signs or a log, the nonlinear function log. Well, one important feature of the Ricci curvature is that it gives us a special representative in the canonical cohomology class, the first term class, up to a certain coefficient, 2 pi. Well, because of the importance of the Ricci curvature, in 1950s, as early as the 1950s or 60s, people have been interested in this so-called prescribed Ricci curvature problem or prescribed volume problem on a Kahler manifold, a compact Kahler manifold. Well, these two problems can be described as follows. Well, the first problem is the prescribed volume form. You simply say that for given any smooth volume form on the Kahler manifold, can we find a Kahler metric in a given Kahler class? So that its volume form is exactly the given one. Well, this is the first problem on a Kahler manifold. And the second one is the prescribed Ricci curvature problem. Essentially, it says that, this is, by the way, the famous Calabi conjecture. It asks that for any smooth representative, I write this alpha as the closed one form. For any smooth representative in the first term class, the question is this a given representative, the Ricci curvature of certain Kahler metric in a given Kahler class? Well, it turns out by the definition of the Ricci curvature of a Kahler metric that these two problems are essentially equivalent. They are both reduced to the most important nonlinear PDE on Kahler manifold, the so-called complex Mondiampere equation. Well, let's now come to the precise equation. By the DD-bar lemma on a Kahler manifold, any Kahler metric in this Kahler class, as we learned from the talks from last week, that any Kahler metric in a given Kahler class can always be written as the Kahler metric plus DD-bar of certain smooth function. And we denote this metric by omega. So the previous two problems are both equivalent to the wedge product of the metric omega by itself for n times equal to the given smooth volume form. Well, because this equation is, the Kahler, if we view the equation as an equation of the unknown function phi, the so-called Kahler potential, then this Kahler potential is uniquely defined up to adding some constant. So we may, to fix the uniqueness of solutions, we just normalize the Kahler potential so that its supremum is equal to 0. Well, of course, there are other equivalent normalizations. For example, if you take the integral of the phi to be 0, that's another normalization, very frequently used normalization as well. Well, so now let us focus on this Mondiampere equation. In local coordinates, this equation can be written as the if we view this, if we recall, we write the GID bar as a local coefficient of the Kahler metric. This equation can be written as a determinant of GID bar plus the ordinary Hessian, complex Hessian of the Kahler potential phi equal to the right-hand side. Even though this equation is locally expressed, but this is in fact the global equation because the determinant, both of the determinant on the right, both sides they change accordingly. They change it similarly. We take the holomorphic coordinates change. Well, for this equation to be solved, one immediate requirement is if we integrate both sides, because of the Stokes theorem, the integral of the left-hand side will always be equal to the integral of omega x to the power n. So one immediate compatibility condition or necessary condition for this equation to be solvable is the integral of the function e to the f should be equal to the total volume of the given metric omega x. Well, it turns out this necessary condition is also sufficient by the famous theorem of Professor Yao, that this equation always admits a unique solution whenever the function f satisfies this compatibility condition. Well, Yao's proof relies on this so-called continuity method. We deform this Mondiampere equation by writing a parameter, by writing it as a family of complex Mondiampere equations by multiply this f by some factor t, parameter t, and then you deform the t from 0 to 1. You can eventually solve this complex Mondiampere equation. And one of the most technical points in the proof is that relies on this standard a priori estimates in the PD theory, especially the C0, C2, and higher order estimates. Well, Yau's theorem is already tells us the importance of the a priori estimates or the analytical a priori estimates on Kahler geometry. Well, among them, all these a priori estimates, the C0 is the most technical one. Well, Yau's original proof depends on the Moser iteration argument. After Yau's proof, one of the a major advancement on complex Modigliani equations is the theorem due to Kahler, who proved that for the C0 estimate or the infinity estimate of the Kahler potentials, whenever the function on the right hand side, e to the f, is LP norm is bounded. Here, we only need this p to be strictly bigger than 1. I recall L1 is just the compatibility condition. And Kahler's theorem say that we only need the LP norm for the function on the right hand side, then we can again get the L infinity estimate for the Kahler potential. Well, in fact, we can even get more on the regularity of the Kahler potentials from the works of Kahler, Demailly, and other co-authors. That in fact whenever the function on the right hand side satisfies this LP norm bound, then the Kahler potential phi itself is in fact Holder continuous, with the Holder exponent depending only on the complex dimension n and this Holder exponent. The LP exponent p. Well, also I want to remark that in Claudius' theorem, this p strictly bigger than 1 is in fact sharp. You cannot get this uniform estimate for p equal to 1, just as in the compatibility condition. Here's the standard example. If we consider this so-called Flory green function, well, in general it doesn't exist, but we can approximate this kind of function locally. This function satisfies, for a given point z0 on the manifold, it is locally like log of the z squared up to certain bounded functions. And we know its Modigliani mass at the point z0 is approximately the delta function. And the delta function is famously known to be L1, but not in LP for any p bigger than 1. And you can see this Green's function has log pole. Or you can just regularize this Green's function a little bit to make it smooth. Again, you cannot expect L infinity or C0 norm bound on this regularization of the Green functions. So this p bigger than 1 is indeed sharp. Well, for let me mention a few remarks on this analytical estimates for the more complex Modigliani equations. Claudius proof his method relies on this so-called potential theory, which is a very powerful tool when you study the non-smooth quasi-plurisample functions on Kahler manifolds. And this approach has the advantage that it can be further extended to the degenerate case. Degenerate case, what I mean is when you allow the background Kahler matrix to degenerate to the boundary of the Kahler cone. It has been extended to those more general cases by the works of Asadil Giazirahi and Demailly independently. Well, essentially, the extensions again relies heavily on Claudius' original approach. The L infinity estimate for singular or degenerating complex Modigliani equations turns out to be very important in complex differential geometry. Let me just mention a few applications. Of course, there's a far large list of applications. The first one is on the Kahler-Ritchie flow, and also on the degeneration of Calabi-Yau matrix, as we have seen from the talk of Valentino Tossati last week. Well, as far as I know, there are other approaches for deriving this C0 estimate or L infinity estimate for complex multi-ampere equations. The first one is, of course, by Yau's original Moser iteration argument. And the second approach is by this ADP maximum principle, suggested in a paper of Chen and Yau, and written down by this Blonsky. And also the last approach that I know is due to myself and Fong and Tong, when we apply this auxiliary complex multi-ampere equation technique. And one of the benefits is that it applies to more general fully nonlinear PDEs on Kahler manifolds. So those are the analytic estimates or the analytic set of the Kahler matrix, essentially on the estimates of the Kahler potentials. Well, what about the geometry or the geometric estimates for the Kahler matrix? Let me just mention preliminary results that was done by myself in the joint works with Xinfu and Song. The result can be summarized as follows. Say again, if we have a compact Kahler manifold, fix the compact Kahler manifold, and then for any Kahler metric, as long as its Kahler class is bounded in some way, and assume that the function, the volume form, the normalized volume form of the Kahler metric omega, it satisfies this Claudier-Tapp integrability condition. The LP norm of e to the f is bounded. And furthermore, if we require that the Ritchie curvature of the metric is bounded below, then we in fact have the diameter upper bound for the metric. Well, one thing is that the main point of the results is that the diameter of X depends only on the given parameters without the explicit upper bound on the Kahler metric itself, but only on the Kahler form itself, the Kahler class itself. Well, this theorem, of course, is empty if we require the Ritchie curvature is strictly positive, because this result holds by the classical Bonding-Mayer's theorem in Riemannian geometry. And for Calabi-Yau matrix, that is for Ritchie flat matrix, this kind of results have been established in the works of Ron and Zhang and Tossati. And also, we cannot expect such results for Riemannian manifolds because the total volume bound plus the Ritchie curvature bound is not enough to guarantee the diameter bound, because we can consider a thinner and thinner and larger torus as a counterexample. Well, so this kind of theorem suggests that we can indeed get some geometric information for a Kahler metric from its total volume. However, and together with the Ritchie lower bound. However, in most geometric problems on Kahler geometry, we know the Ritchie curvature in general is not bounded below. So one naive guess is that, as I mentioned earlier, that the Ritchie curvature of a Kahler metric is essentially the DD bar of the volume form. So we may expect that the volume form itself, without taking the DD bar to get the lower bound, the volume form omega n to the power n itself is already sufficient to give us some geometric information on the kilometric. Well, some preliminary results has been known. For example, the diameter of the metric is usually bounded, assuming that if the metric is in this fixed Kahler class, and together with a certain bound on its volume form. I use this bound L1 log L to the power P. I will explain this notation later. It's just some stronger integrability condition than the nearly L1 norm bound. Well, this is done in the works of Li and myself with Feng, Wang, and Tong. When we derive this uniform, not uniform, the modulus of continuity estimate for the Kahler potentials, previously known to be Holder continuous from the works of Demai, Kolodji, and other guys. Well, this kind of technique to derive the diameter bound relies on the modulus of continuity of the Kahler potential. In general, this is not known if the Kahler classes degenerate. So it's not so useful for study the singular Kahler matrix. Well, so now let's move on to the main results. Well, again, I need to fix a few notations for the next presentation. Well, again, let's fix the Kahler metric, x and omega x. And without loss of generality, we may normalize the total volume to be 1. I use the v of omega x to denote the total volume, maybe up to certain n factorial as in the standard textbooks. Well, for any Kahler metric, I use the curl x to denote the space of all the smooth Kahler metrics, and we denote the f omega to be essentially this volume form or the volume function of the metric omega, and I normalize it by divided by v of omega. V of omega is just the total volume of the Kahler metric omega. So this e to the f omega is essentially a probability measure on the Kahler manifold. Well, for any p bigger than n, we denote this so-called p entropy as the LP norm of the function f against this probability measure e to the f omega x to the power n. And this is what I mean by this L1 log of L to the power p norm of the function e to the f. So this is essentially the LP norm of the function f against the measure defined by omega to the power n. Well, given certain parameters, positive numbers a, k, and p, we define a subset of the space of Kahler metrics as the collection of the Kahler metrics whose p entropy is bounded by the number k, and also the intersection number of the Kahler classes omega with omega x to the power n minus 1 is controlled by the number a. Well, essentially, this condition, this intersection number upper bound is essentially give us the control of the Kahler class of the metric omega. As can be seen from the previous, the next remark, that this intersection number bounds just to give us this natural representative theta in the Kahler class, which is bounded in any CK norm. The point is that this theta may not be Kahler itself, but it's only a smooth closed one form. Well, so we fixed those notations, And we're going to work on the associated Green's function, not a Fourier Green's function, but it's just a standard Green's function on the Kahler manifold. Let me just first recall the definition of the Green's function. For a compact Riemannian manifold without a boundary, we know the Green's function associated to the standard Laplacian always exists. And it is defined by the following equation. For any fixed x, the Laplacian of the Green's function is essentially the minus delta of the function. We add the constant 1 over v, the total volume, to make this equation compatible. And the Green's function, of course, is defined up to some normalization. So our normalization is we require that the integral of it equal to 0. The Green's function always exists, as seen in the book of Yao and Shun on this lecture on differential geometry. And we also know the Green's function is always a smooth function on the product away from the diagonal, and it's also symmetric. And locally, when x and y are close enough, it is equal to 1 over the distance to the power real dimension minus 2. Well, assume the real dimension to be bigger than 3. When the real, if on the Riemann surfaces, we know the Green's function so locally looks like the minus log of the distance function. Well, for the classical result of Chen and Li, that on a Riemannian manifold, if you further put some condition on the rich lower bound, then we have a uniform lower bound on the Green function. The lower bound of the Green's function depends on the diameter and also the total volume. Well, so this is our first results on the estimate of the Green's functions. You see that given the parameters, the a, k, and p, we are able to find some constants, say some constant c, that depends only on the given parameters. And also two constants, epsilon 1 and epsilon 2, that depends only on the complex dimension, and also this the exponent p in this p entropy. Not the p entropy itself, but only the exponent p. Such that for any smooth Kahler metric in this subset, the Green's function satisfies the Green's function associated to the Kahler metric satisfies the following estimates. That is, we have the uniform lower bound, depending only on the constant c divided by the total volume. And also we have the integral bounds on the Green's function up to a certain normalizing constant from the total volume. We have the integral, essentially this sum LP bound on the total volume, on the Green's function, and also the sum LP bound on the gradient of the Green's function. Well, later on I will explain how this kind of integral bound, uniformly integral bound on the Green's functions lead to some geometric estimates on the Kahler metric. And for some further remarks is that if furthermore, instead of the p entropy bound on the total volume, on the volume function, if we assume the LP norm bound, certain p bigger than 1, then those exponents epsilon 1 and epsilon 2 can be chosen as sharp as we expect for the Green's function. Those numbers, those exponents n over n minus 1 and 2 n over 2 n minus 1 is sharp for the Green's function for the integral estimate on the Green's function, as can be seen from the Euclidean case, for example. Well, certain geometric information can be derived from the previous estimate on the Green's functions. Let's take the same assumptions as in the previous theorem. Then for any such Kahler metric, omega, we have the following geometric estimates. First, the diameter upper bound, and second, on the non-collapsing, local non-collapsing of the geodesic balls. For any point x on the manifold, the volume of the geodesic ball of radius r divided by the total volume is bounded below by some constant times the radius to some power alpha. Well, we can of course make sure that it's alpha to be as close as to the sharp one, 2n. But unfortunately, we are not able to achieve this sharp estimate. This alpha can be taken as any number bigger than 2n, but in general, we're not able to prove it to be exactly equal to 2n. And also, we have this Sobolev inequality, uniform Sobolev inequality for any Lipschitz function, or in more general, W1pf function. We can find some number q that is bigger than 1, which satisfies this uniform Sobolev estimate, Sobolev inequality on the Kahler manifold x omega. Well, again, this Sobolev inequality can be made as sharp as enough if we take the LP norm of the function e to the f omega. Well, for some remarks, in our previous works, we have to impose some additional assumption on the lower bound of the total volume, on the volume function. For the lower bound gamma, for the gamma, where gamma is the continuous non-active function, whose vanishing locus is very small. For we need the Hausdorff dimension of the vanishing locus to be smaller than 2n minus, well, it should be 2n minus 1, by the way. Well, this condition in general holds for most geometric problems, including the singular Kahler matrix. So the previous extra assumption, in fact, applies in the geometric settings. This extra assumption was later removed independently by ourselves and Gage and Toh last year. And a similar diameter estimates for the Kahler currents on big cohomology classes was also derived by Du Wu using the Dean-Sibony Sobolev space theory, and also the Sobolev inequality in our earlier works. Well, let me summarize what can we conclude from the previous, conclude immediately from the previous two theorems. Well, in summary, what we get is that as long as the Kahler class is bounded in the Kahler cone, and as long as the relative volume function is integrable, slightly stronger than the L1, then we have the estimates. We have the uniform estimates on the Green's functions, on the diameter, on non-collapsing, and also the Sobolev inequality hold for such metrics. Well, one immediate consequence is the pre-compactness theory, pre-compactness in the Gromov-Hausdorff topology for the space of Kahler metrics in this subset of Kahler metrics. The diameter and the non-collapsing estimate immediately tells you that for any sequence of Kahler metrics in this subset, up to a subsequence, we can always take the Gromov-Hausdorff limit to some compact metric space Z dz. Well, in general, it's a natural question to identify what this Z look like. I think this is largely open at this moment, but there are some partial results in this direction if we assume the rigid curvatures are bounded in some weak sense, which I will explain later. Well, there's some other applications of the previous theorems are to this parabolic complex Monge-Ampere equation. The Kahler flow is defined to be if we evolve the Kahler metric in the Kahler matrix in the direction of minus Ricci with the initial given by a Kahler metric omega 0. For this parabolic Monge-Ampere equation, it has been known that this equation admits a solution up to the time t, where this time t depends only on the cohomology classes when the initial class plus t times k of x. As long as these Kahler classes are Kahler, we know the Kahler flow can be solved up to this time t. Depending on whether this t is finite or infinity, this Kahler flow is called finite time, short time existence or long time existence. For an application of our previous theorem, in case we have a short time existence when the final time or the maximal existence time t is finite, additionally, assuming that the limiting Kahler class is big, then we know all the Kahler metrics along this Kahler-Ricci flow belong to our subset, the subset in our previously defined Kahler matrix. In particular, those metrics satisfy all the geometric estimates I just mentioned in the previous theorems. Well, additionally, in case this time t is infinity, that is equivalent to this k of x. K of x is the canonical line bundle. This canonical line bundle is nav. Then for the normalized Kahler field, normalized for convenience, I just subtract the original equation by omega. This normalized Kahler flow is still belongs to the subset of V in our notation of the Kahler matrix. Well, again, all the previously mentioned estimates hold for such metrics as well. Well, so those are the applications for the Kahler-Ricci flow. For the long-term Kahler-Ricci flow, there are some previously known results. First of all, the upper bound of the total, the volume function just to follow the pointwise upper bound, just to follow straightforwardly for maximum principle, and under the stronger condition that Kx is semi-ample, not just enough, then the diameter estimate was previously obtained in the work of Wang Jian and Jian Song, who also proved it's the Gromov-Hausdorff convergence and also identified the limit, the Gromov-Hausdorff limit along this long-time Kahler-Ricci flow. Well, of course, let me just mention this famous conjecture in birational geometry. It is conjecture that in case x is projective, then the nafness and the semi-ampleness should be the same. So if we assume the abundance conjecture, then the previous work has been proved in the work in the paper of Jian and Song. Well, I also want to mention some applications to some applications of the previous theorems to the CSCK matrix. The theorem states as follows: it's proved in the journal works with Fong, Song's theorem, and also Jian and Shi and Song. The theorem states that assume again x is the compact Kahler manifold, and assume that the Kx is semi-ample. Then for any fixed Kahler class, we can always find some small interval starting from the kx in the direction of omega x, such that in each such Kahler class, we can find a unique CSCK metric, omega delta. And this omega delta satisfies the diameter upper bound estimate. Well, the existence of the CSCK matrix was previously proved in the work of Jianshi and Song, which relies heavily on this criteria of Chen and Cheng. Well, now let's look at some estimates on singular Kahler space, normal Kahler spaces. Well, because of the uniformity of the previous theorems, enables us to develop certain tools on the geometric analysis for Kahler spaces with mild singularities. Well, here's a basic setup. Assume that we have a normal Kahler variety. Normal simply means that we have a precise definition, but intuitively, the normal simply means the singular set is very mild, has at least the codimension 2. Well, we are going to look at the singular Kahler matrix omega on the Kahler space X that satisfies the following regularization conditions in some sense. Say, for the Kahler variety, we fix a Kahler resolution from some Kahler metric to from some Kahler manifold to the Kahler variety X, and we fix the smooth Kahler metric on the Kahler manifold Y. Well, we look at the singular Kahler matrix on X that satisfies the following conditions when we look at the pullback of the singular metric. First of all, assume that the cohomology class, so the intersection number is bounded, and also the relative volume function of the pullback on the manifold Y satisfy this P entropy upper bound, just analogous to our previously defined entropy function. But this time we just look at the pullback instead of the metric itself. And furthermore, we just impose some technical assumption, which is in general not necessary, but for our convenience, and also it holds for mostly known examples. We assume that this F omega has log analytic singularities. Essentially, a more general example appears in Yao's original paper on Kahler conjecture, that if we look at the function locally like the product of the holomorphic sections, this is a particular example of the analytic functions that we are interested in. Well, for the Kahler metric, from the previous, from the definition of the singular matrix that in the previous slide, the regularity of the complex multi-ampere equations immediately tells you that this metric omega is in fact smooth on the regular part, together with the zero or the locus set of this F omega. Essentially, we have an open dense set X0 equipped with the metric omega, which is smooth, and X0 is open dense in the manifold X, in the Kahler space X. Well, this X0 equipped with omega is not complete. It's an incomplete Riemannian manifold or Kahler manifold, and we take the metric completion and we denote the metric completion by X hat, and we denote the induced distance by d omega, equipped with the measure induced from the metric omega. Well, we have the following uniform estimate on the metric completion. Well, first of all, the diameter of this metric completion is uniformly bounded, and the sublevating qualities still hold for this metric measure space. And furthermore, there exists a unique P-kernel of the standard Laplacian of the metric omega. We take the extension of this Laplacian operator. There exists a unique P-kernel which satisfies this upper bound for this number Q, for this exponent Q, which comes from the uniform Sobolev inequality. And also the eigenvalues of this Laplacian operator is discrete, and it satisfies this uniform lower bound for any lambda k. We order the lambda k increasingly, accounting multiplicity. Well, this is our theorem holds for any Kahler varieties equipped with the singular Kahler matrix defined previously. For projective varieties with the smooth Bergman matrix, the P-kernel and eigenvalue estimate was previously established in the paper of Peter Lee and Tian. Well, let me mention a final application of the previous the estimate for the singular matrix. Suppose we have X to be a normal projective variety with mild singularities, like KLT singularities. Suppose that the first term class is 0 or negative. For the singular varieties, the existence of the canonical match singular matrix has been known from the work of Gadget-Zararaki, Gadget-Zararaki. And we know from our previous theorem, we conclude from our previous theorem that the unique Kahler-Einstein occurrence satisfy that the diameter of those metric completions is in fact bounded. And also our previous estimate, like the Sobolev and the Laplacian, the eigenvalue estimate still hold for such metric completion, because we can easily check that this singular Kahler-Einstein metric satisfy our previous conditions. Well, again, the natural question is to identify the metric completion of the singular metric. And in fact, from a very recent work of Gabor Zaghli-Edey, that we know that in this metric completion, the metric completion is in fact homeomorphic to the normal variety itself. Well, for this singular Kahler-Einstein matrix. Well, let me just mention some further results on this singular Kahler matrix. Well, those are some results summarized from the works of many people, from Zaghli-Edey, myself, and Song, and Chen, and Chu, and several more people. Well, the results can be summarized as suppose X is a compact Kahler normal variety with log terminal singularities. And also assume that we have a resolution from some smooth Kahler manifolds such that is the anti-canonical line bundle is relatively naive. And also assume that we have a singular metric in the set that satisfies our previous integrability conditions on the volume functions. And also assume that the Ricci curvature of such metric is bounded below in the current sense, because this metric is singular. We need to make the Ricci curvature or Ricci current well defined, and also define the lower bound of this Ricci current in the weak sense. Then we have the following. First, this metric measure space of the regular set. This x hat is essentially the metric completion of this omega on the smooth part of the metric of the space X. The metric completion is in fact non-collapse RCD space that is homeomorphic to the normal space X itself. And also we have this metric irregular set of X hat. It should coincide with the regular set of X as the analytic variety. Well, this metric irregular set is just like the collection of the points whose tangent cone is isomorphic to R2n, as in the talk of Professor Zhu for this Alexander spaces. But this tangent cone is defined in the Gromov-Hostov sense. And furthermore, we have this omega is the Kahler current. Kahler current means it's bounded below by some smooth Kahler metric on the singular Kahler variety X. Well, this as mentioned in Professor Zhu's earlier talk, the RCD space is in fact some metric space that satisfies the generalized Ricci-Lower bound. In fact, there are certain equivalent characterization of the RCD space from Honda's result that the RCD space can be characterized as the Ricci curvature is bounded in some weak sense, together with two facts. The eigenfunctions are ellipses, together with some uniform Sobolev inequality. The first part is proved by verifying that the eigenfunctions of the Laplacian operator on the limit is in fact smooth. Is in fact ellipsis. Well, the Kahler condition of this kind of singular Kahler metric is the Kahler current condition is in fact previously known for smoothable singular Kahler-Einstein metrics by the work of Gage, Gournancier, and Zirafi. In the previous theorem, we need some special requirement on the resolution of the metric, the resolution of the Kahler space X, so that the anti-canonical class is relatively naff. Well, in fact, this condition can be removed in dimension 3 by recent work of myself with Xinfu and Jian Sao. So those are the main results. So let me explain in the last 5 minutes quickly the proof of this kind of results. Well, as I mentioned, the Green's function, the uniform integrability conditions on the Green's function is very useful to derive is enough to derive this geometric estimate on the diameter and also the non-collapsing. The diameter bound can be derived as follows. See, assuming the Green's function, the gradient of the Green's function satisfies this uniform L1 estimate, we just take any 2 points that realize the diameter, whose distance realize the diameter, and we write the function rho as the distance to any of the fixed points, and we just apply the Green's formula twice. First, apply the Green's formula to the point x0. We get this integral equation, and then we just apply the Green's formula to the point y0. Immediately, that give us the diameter estimates. Because the first equation tells you the integral of the distance function is essentially bounded by the gradient of the Green's function, and just apply that estimate to the first term, and then this guy again is bounded. So that is the diameter bound, assuming the gradient of the Green's function is bounded. Furthermore, if we have some stronger conclusion on the gradient of the Green's function, then we just apply a very similar argument. We take a cutoff function on the geodesic ball, a standard cutoff function, which is constantly 1 on the half ball. And then we just apply the Green's function to Green's formula to the function rho times eta, and then argue similarly applying the Holder's inequality. That will follow straightforwardly. Well, so all those estimates rely on the analytic estimate on the Green's function, the uniform integral estimate on the Green's function. So now we focus on the estimates for the Green's functions. The idea is simply based on the previously developed approach of the comparison of the equation with certain auxiliary complex multi-ampere equations, as done in my work with Fong and Tong. Well, we are going to adapt this nonlinear approach to the linear equations. Nonlinear approach means we use the auxiliary complex multi-ampere equation, which is fully nonlinear. And linear equation simply the Green's function satisfies this linear equation, the Laplacian of the Green's function. Well, those are just a technical part. Even though we didn't work directly with the multi-ampere equations, but as in the definition of f omega, we can view this omega as the solution of this complex multi-ampere equation. And then we are going to look at the Kahler potential phi as some estimate on the Kahler potential phi. Well, one of the key in the estimate is this mean value type inequality for the linear equations or for the linear inequalities associated to the Laplacian of the kilometric omega in this subset. So suppose we have a smooth function or L1 function v, which satisfies this Laplacian lower bound in some subset, the sublevel set omega s of the given function v. Then we have the supremum of v is bounded essentially by the integral of the function v. And this is the typical mean value type inequality. If you have the Laplacian lower bound together with the Ricci curvature lower bound, then we always have the supremum of v is bounded above by the average of or the integral of the function v. This type of a mean value inequality usually requires the Ricci lower bound. For example, in the paper of Li and Sean. Well, so now let's look at a rough idea in the proof of this key lemma. Well, we take this auxiliary complex multi-ampere equation given the function v. We solve this complex multi-ampere equation on the Kahler manifold, and this eta k is just a smoothing of the function v minus s to make the right hand side positive and smooth. And this equation always admits a smooth solution by the celebrated work of Yao. And we take the constant a as the normalizing constant to make this equation compatible. And we define a constant lambda that depends only on the Kahler potential, the upper bound of the Kahler potential, and look at this comparison function. This comparison function is one of the key observations in this approach. And we can apply maximum principle to show directly that with appropriate choice of the constants lambda and epsilon and lambda, we can actually show that this capital phi is in fact negative. So once the phi is negative, then together with the exponential integral estimate on the Kahler potentials, we are able to show that this monotone function phi of s is in fact satisfy this uniform integral estimate. And then the Georgia tab iteration argument, we are able to conclude that this function phi is in fact empty, is in fact 0 when S is sufficiently large. And this upper bound S infinity can be computed as follows. Then immediately it follows that the supremum is bounded above by that constant. Well, it should be enough by in 1 minute. And then just apply the lemma first to the Green's function, the normalized Green's function. We immediately infer that the Green function, the minus of the Green's function is bounded by the integral of the Green's function. Furthermore, if we apply our key lemma twice to any function, a smooth function, v whose Laplacian is bounded by 1, we in fact have this L infinity bound of the function v. And by essentially a repeated use of auxiliary functions that in the proof of the key lemma, we are able to conclude that for any such v, we have the uniform integral estimate on the v as well. So once we have that, immediately we will get the lower bound of the Green's function. For example, if we solve again a linear equation with h being this characteristic function of the negative part of the Green's function, and then apply the Green's formula together with the upper bound of the function h of k, we see that this vk is uniformly bounded, and the vk in fact converge to the integral of the Green's function over the negative part of the Green's function. So that will give us the uniform estimate on the Green's function. Together with the normalizing condition, we have the uniform L1 bound on the Green's function. And with some more technical work, we can improve this kind of uniform estimate from L1 to LP, and also to the LP estimate on the gradient of the Green's function. So I will stop here. Sorry for out of time.